So in the last session, we were talking about how to do the design of isolated rectangular footing. So in this particular session, we are going to focus on how to do the design for isolated square footing. That's what we are going to focus on. So here you can see the problem statement: a solid footing that has to transfer a dead load of 1000 kilonewtons and an imposed load of 400 kilonewtons from a square column. So the column size you can see here, 400 by 400, which is a square column. So assume that Fe415 grade of steel is used and M20 grade of concrete is used, and the SPC of the soil is 200 kilonewtons per square meter, and the allowable settlement is 25 mm. So this is the data. So we know that for a square column, it is required to design the square footing, and for a rectangular column, it is required to design a rectangular footing. That's what the thumb rule we have been talking from the first session onwards related to the design of footing. So when it is a square column, we try to design mostly the square footing. When it is a rectangular column, we try to design mostly the rectangular footing. So in this case, if you observe, the type of the column is the square column, which is 400 by 400 mm. So since it's a square column, what I'm going to do is I'm going to show you how to design a square footing. Okay, how to design a square footing. So the same steps will be there. There won't be any much changes with respect to the steps. So let me just talk about the steps and the process of solving this particular problem. So the first parameter is we need to find out the loads that are coming onto the structure. So what are the loads? So in this case, we have two types of loads. One is called as a dead load and the second one is called as imposed load. So dead load plus live load. Imposed load is also called as live load. So dead load plus imposed load equals to 1000 plus 400 kilonewtons. So that gives 1400 kilonewtons of dead load is, 1400 kilonewtons of load is coming onto the structure. Now we know that the self weight of footing. So how to calculate the self weight of footing? So self weight of footing equals to 10% of column load. Okay, whatever the load that is coming from the column, in that load, 10% has to be considered as self weight of footing. So that equals to 10% of what is column load? Column load is 1400 kilonewtons. So that will be 1400. So that equals to 140 kilonewtons. So this is the amount of self weight of footing. So from this, we can calculate the total load transferred to the soil. So total load transferred to the soil equals to 1400 kilonewtons. That is the total amount of load plus the self weight of footing. What is the self weight of footing? It is 140. So that equals to 1540 kilonewtons of load. Okay, this is the total amount of load that the structure or that the footing will transfer to the soil. Okay, this is the total amount of load that will get transferred to the soil. So from this, what we can do is we can find out the area of footing. So we can call it as required area of footing. So how to calculate the required area of footing? Required area of footing equals to, so total load. Okay, total load transferred to the soil, that is 1540 divided by the SBC of soil. What is SBC of the soil? It is 200 kilonewtons per square meter. Okay, the SBC of the soil is 200 kilonewtons per square meter. So the total load divided by SBC of soil equals to, that will become 7.7 square meters. So this is the area of the footing. Now from the area, we have to calculate the length and width of the footing. Okay, from the area of the footing, we have to calculate length and width of the footing. Now here, it is a square footing. Okay, since we are designing, the square footing, actually in the design of rectangular footing, we have considered the projection length as x, right? What is x? So the distance from all the sides of the column should remain same so that uniform pressure distribution will happen. But here it's a square column. So square column will have the same amount of distances on all the sides. So we don't need to look after the factor called projection, that is x value. If you remember, in the previous sessions, we have talked about this projection, that is x value, right? This projection from all the faces of the column. Now, since it's a square column, we don't need to bother about the projection here because on all the sides, the distance will remain same. So here we can directly calculate the length and width of the footing. So how to calculate the length and width of the footing? As we are designing the square footing, we don't need to consider the projection. Okay, we don't need to consider the projection on all sides of the column. Why? What is the reason for that? The reason is for square column. Okay, for square column, all sides are equal. So this for square column, all sides are equal, and hence the projection will also be equal. Okay, this is the consideration. The projection will also be equal. So that's why we don't need to consider the projection for the calculation of square footing design. So on all sides, right? So now how to calculate the length and width of the footing? So the length and width of the footing we can calculate as square root of this one. Okay, square root of area will give the area length and width of the footing. So let's say providing square footing. Okay, we are designing the square footing. So providing square footing, that is length of the footing equals to width of the footing equals to square root of, okay, let me call it as square root of, let me just insert the symbol. Just give me a second. Yeah. So square root of area. What is area? 7.7 square meters. So when you do 7.7 square meters, the value will become 2.77 meters. Okay, 2.77 meter. Since we are designing the square footing on all sides, since we are designing square footing on all sides, the side remains same or the dimension remains the same. So therefore, what I'll do is, it is not possible to provide exactly 2.77. So I will round off this value to 2.78 meters. To the nearest value, I'm just rounding it off. That is 2.78 meters. Or you can also go with 2.8 meters also. For better calculation, you can go with 2.8 meters also. Anyways, let me go with 2.8 meters only. So therefore, length of the footing LF equals to width of the footing BF equals to 2.8 meters. Okay, 2.8 meters. So this is how we can calculate length and width of the footing for the design of square footing. But whereas for rectangular footing, we have seen how to calculate that one. First, we have to consider the projection span, and then we have to calculate a plus 2x and b plus 2x. Then only we are going to calculate the length and width of the footing. But in square footing, we don't need to work with the projection, because for square footing on all sides, it is same. Right. So therefore, provided area of footing equals to provided area of footing equals to, what will be the provided area? 2.8 into 2.8. That is length of the footing into width of the footing. So 2.8 into 2.8, that will give you 7.84 square meters. Okay, 7.84 square meters. So this is how we can calculate the area of the footing. Now, the next thing is we have to calculate the upward soil pressure. Okay, upward soil pressure. So how will we calculate the upward soil pressure? We have decided that in the last session. So upward soil pressure equals to the total load. Okay, total load. What is total load? 1540. This one. So the total load divided by the provided area of a footing. What is provided area? 7.84. So total load divided by provided area of footing. So what is the total load? Total load is 1540 divided by the provided area of footing is 7.84. So that will give us the upward soil pressure value. That will become 196.43 kilonewtons per square meter. Okay, kilonewtons per square meter. So that's how we can calculate the upward soil pressure. Now, the next step we have to do is just let me write that. The next thing that we have to calculate is the depth of the footing. Okay, depth of the footing. So we know that in the last sessions we have talked about, so the depth of the footing is majorly influenced by two criteria. What are they? The first criteria is called as a flexural criteria, the flexural criteria, and the second one is called as shear criteria. The flexural criteria and shear criteria, these are the two criteria where the depth of the footing will get influenced. Now, what we will do is we will calculate the depth of the footing based on flexural criteria. After that, we will check for the shear criteria. That is, check for one-way shear and two-way shear. That we will see in the end. So first, let us calculate the depth of the footing based on flexural criteria. So how to decide the flexural criteria? Here, the moment along x direction and the moment along y direction. That is moment along length and moment along width. So here I'm just calculating as or considering as mx and my. Mx represents moment along length and my represents moment along width. So here, in order to calculate the moment along x and y directions, we don't need to have the direct formula substitution. What we can do is we have a specific formula. What is that formula? That I'll talk now. So here, before talking about that formula, let me just draw the image of the footing. So if you see, or if you consider this as the footing, a square footing. Yeah. So this is the square footing, and here you have the column. Okay, a square column is available. Now, usually moment will be acting. Okay, usually for a square footing, not for the rectangular, but for the square footing. So for square footing, the moment will be acting, or the maximum moment will be acting at the face of the columns. Okay, at the face of the columns, the moment will be acting. These faces of the columns, the moment will be acting. These are the faces of the columns. Now, what we have to do is we have to find this distance. Okay, we have to find this distance. Then we can directly find out the maximum moment that is acting. Okay, the maximum moment that is acting. So this distance calculation is very much important in the moment calculations, especially in the square footing, not in the rectangular footing. In the rectangular footing, we have a different process, but in square footing, we have a different process. So how to calculate this distance? So what is the length of the footing? So length of the footing is 2.8 meters. Okay, and width of the footing is also 2.8 meters. And the size of the column, what is size of the column? The size of the column is 400 by 400 mm, which is provided in the question. So that will become, so let me write it here, 0.4 meters. This is the size of the column. And this is another side of the column, 0.4 meters. So now we should calculate this distance. Okay, we should calculate this distance. So how to calculate this distance based on the dimensions that we have? So 2.8, okay, 2.8, let me write it here. So 2.8 minus 0.4, that is the size of the column. So 2.8 minus 0.4 divided by 2. Okay, 2.8 minus 0.4 divided by 2. 2.8 minus 0.4 will become 2.4. Okay, 2.4 upon 2, that will give you 1.2 meters. Okay, that will give you 1.2 meters. So this distance, okay, the maximum moment will be acting at a distance of 1.2 meters. Okay, 1.2 meters. This is very important in the calculation of square footing design. In the rectangular footing, we did not do this one. Only in the square footing, this factor comes into picture. Right? How to get this factor? Let me rewrite all these things once again. So we have a square footing. Okay, we have a square footing, and then we have a square column inside it. So what I am telling is the moments will be acting, the maximum moments will be acting at the face of the columns, along this face, along and also along this face of the column, on either faces. Okay. Now our intention is to calculate what is the distance between these two from the face of the column to the face of the rectangular footing, square footing. This distance we have to find out. Okay, this distance we have to find out. So how will you find out? We know the length of the footing, that is 2.8 meters, and we also know the width of the footing, which is 2.8 meters, and we know the size of the column, that is 0.4 meters along this side and 0.4 meters along this side. So in order to calculate this distance, okay, in order to calculate this distance, we have the formula that is 2.8 minus, that is total length of the footing, minus the size of the column, that is 0.4 meters, divided by 2. So this will give you 2.4 divided by 2. That will take us to the value of 1.2. So at a distance of 1.2 meters, okay, this distance is 1.2. So at a distance of 1.2 meters, the maximum moment will be acting on the column. Okay, the maximum moment will be acting on the column. So this is very important in calculation of square footing design, right? So from this, remember this value, it is 1.2 meters. So from this calculation, we are going to calculate the moment along x direction and moment along y direction. See, the distance along length direction will become 1.2 and the distance along y direction will also become 1.2 because it's a square column and square footing. So we don't need to separately calculate this distance again. Both distances will remain same, which is 1.2 meters. Right. So now let us calculate for the moment along x and moment along y direction. So moment along x or moment along y equals to, that is mx equals to my equals to upward soil pressure, that is 196.43 into the side of the column, side of the footing, that is 2.8, okay, 2.8 into the distance, that is 1.2 square divided by 2. So this is the formula. Okay, 1.2 square divided by 2. So we have already discussed how this 1.2 is coming. So why I'm making it as 1.2 square? It is because we have the value along the left side and we also have the value along the right side. So 1.2 square. So you can simply call it as WL square by 2. Okay, this formula will, you can, if you keep it in terms of structural analysis concept, this formula will become WL square by 2. That's the formula. So if you solve this equation, you're going to get the moment value along x and y directions as 396 kilonewtons meter. Okay, 396 kilonewtons meter. So now let us calculate the ultimate moments, that is mux equals to muy equals to 1.5 times of 396. So 1.5 times of 396 will become 594 kilonewton meter. Okay, 594 kilonewton meter. So that's how the ultimate moments will be coming on x and y directions. Okay, on x and y directions. Now from this, we have to calculate the depth required. So how to calculate depth required? So the depth required calculation, so the depth required calculation depends on grade of steel. It depends on grade of steel. So in our case, the grade of steel is Fe415. So for Fe415 grade of steel, limiting moment of resistance, mu limit equals to, we have the formula, that is 0.138 FCK BT square. So this is the formula to calculate the limiting moment of resistance, especially the depth consideration. So here we don't know the value of D. So therefore, just substitute the values here. We know the maximum moment, which is 594 kilonewtons meter, and FCK is grade of concrete, which is 20, and B is the width of the footing, which is 2.8 meters. Here you can see 2.8 meters, and depth we have to calculate. So once you solve this one, let me write this one. So 396 is the, sorry, 594 is the ultimate moment or factored moment, you can say. 594 into 10 power 6 equals to 0.138 into FCK is grade of concrete into B, that is width of the footing, that equals to 2800 into D square. So based on this, we are going to calculate the depth of the footing. So therefore, the depth of the footing D equals to 277.24 mm. This is how we can calculate the depth. But is it required to provide exactly this depth? No, we have to provide additional depth. Why? Because whatever the depth that we are going to provide, that depth should satisfy both flexural criteria and shear criteria. For flexural criteria, this will be fine. But for shear criteria, this will definitely not be fine. Okay, this depth is not at all required. So what I'll do is I will increase the overall depth. Okay, adopt the or provide the overall depth of the footing. Provide the overall depth of the footing capital D equals to, I'll just make it as 600 mm. I had taken it as 650 mm. So here let us go with 600 mm and let's check whether it will be correct or wrong. Okay, even I am not sure because in some calculations I have taken it as 650 and 700. Let me try with 600 and let's see if there is any error. I'll show you how to modify all these things. If there is no error, then we can directly, yeah.
Sir, overall depth includes both the footing and the column, right?
Yeah, from the ground surface to the bottom surface of the footing. Let me show you that one. I'll just draw. Suppose if this is the column. So if this is the ground surface, from here to here, this will be the overall depth of the footing.
Okay.
Right. So from this, I'm just calculating or considering the overall depth as 600 mm. Let's verify whether it is within the limits or not. Right. So here for footings, we generally provide the cover of the footing as 50 mm, and the diameter of bar usually we'll consider as 16 mm. So let us go with 16. You can also try with 18 mm or 14 mm also. That's not a problem because we are just doing it in manually. So once we go to the CSI safe software, we can do many trials and errors. There won't be any issue, right? So therefore, depth available, you can say it as depth available equals to overall depth, that is 600 mm, minus clear cover, that is 50 mm, minus the diameter of bar divided by 2. So that will become effective depth, that equals to 542 mm. So this is the depth available. So from this consideration, we have to calculate the area of steel. Okay, area of steel or reinforcement.
Sir,
yes.
The cover which you have provided, is it based on any IS code book?
Yes. It is completely based on IS code. If you refer IS 456-2000, so it goes in this way. Suppose, let me write that one. So I'll just make it as cover element or structural element and clear cover. So structural, let's say slabs, beams, columns, and footings. So the numbers goes in this way. For slabs, it is 20 mm, and for beams, it is 20. It should be 25 mm, and for columns, it should be 40 mm, and for footings, it should be 50 mm. These are minimum dimensions, but you can go beyond that also. But mostly in the real-time scenarios, we'll provide these standard dimensions only. So we don't go more than these values. We'll consider these as the maximum values, and we'll provide only these dimensions.
Okay.
So these are as per IS 456 only, not just the random numbers. Correct. So now let us calculate the area of steel based on the depth consideration. So in order to calculate the area of steel, we have a formula that is ASD equals to 0.5 FCK, this formula, so which we have used for the previous session also. 0.5 FCK by Fi times of 1 minus 4.6 mu. What is mu? Mu is the ultimate moment or maximum moment, you can say, which is 594. Yeah, this one, 594 kilonewtons meter. And then FCK is grade of concrete. B is 2.8 meters. That will become 2.2800 mm. And effective depth, the value of D will become 542. This one, D will be 542, and the value of B is 2.8, that is 2800. So let me just write the values here for your calculations. So FCK equals to 20 MPa, and the Fy, that is grade of steel, equals to 415 MPa, and the value of Mu equals to 594, if I'm not right. Yeah, 594 into 10 power 6, 594 into 10 power 6, and then the value of B, that is width of the footing, which is 2800 or 2.8 meters, and the depth of the footing, which we have just got it as 542 mm. So once you substitute all these values in the above equation, the area of steel, we are going to get it as 3174 mm square. Okay, this is basically the area of steel that is based on design requirement. We need to provide this much amount of steel. But in real time scenarios, we don't exactly provide this much of steel. We'll provide some extra amount of steel to take care of additional moments or additional forces that are coming onto the member. So how to find out that extra steel? It depends on percentage of steel. The percentage of steel, that is PT, equals to, we know the minimum percentage of steel. Okay, I'll just make it as, instead of this one, I'll just make it as minimum percentage of steel. Minimum percentage of steel. So how to find out the minimum percentage of steel? We have a formula that is 0.12% B into D. This formula is also again from IS 456 consideration only. So that equals to 0.12% into B. What is width of the footing? 2800 into the depth of the footing we have taken as overall depth, not the effective depth, 600 mm. So once you solve this one, you're going to get the minimum percentage of steel as mm, 2016 mm square. So we have to provide this much, and at least we have to provide this much in order to ensure the safety condition. Now let us provide the reinforcement based upon the diameter of bars we have considered. So what is the diameter of bar we have considered? 16 mm diameter bar. So providing 16 mm diameter bar, say providing 16 mm diameter of bar. So from this, we can calculate the spacing required. The spacing required equals to, you can define it as with the capital S, spacing capital S equals to area of one steel bar. So what is area of one steel bar? Pi by 4 into diameter of the bar, that is 16 square. So pi by 4 into 16 square will give us 201.06, that is area of one steel bar, divided by the total area of steel, that is 3174. The design requirement, not the minimum steel, the design requirement we have to use. So 3174 mm square, 3174, yeah, let it be 3174 mm square into the width of the footing, that is 2800. So that will give us the spacing of the steel as 177.32 mm. So again, we can round off this value to, let's say, minus 20 or 25 mm. Let's go with, I'll just go with 150 mm center to center spacing. So we have already discussed what will happen if you have more length or more distance between the spacing of parts, and what will happen if you decrease the spacing between the parts. The more the spacing, the less will be the number of parts. When the less will be the number of parts, the less will be the forces that will be counteracted. When you have less spacing, more number of reinforcement bars are required, and more number of reinforcement bars are available, effective pressure distribution and effective tensile force distribution will happen. So that's the reason why we have to reduce the spacing. So for spacing, we have to reduce. For the dimensions of the footing, be it square footing or rectangular footing, whatever that is there, we have to increase. Here we have got 2.77 and we increased it. Why? Because the larger the area, the more will be the effective pressure distribution. Similarly, when it comes to the spacing, the smaller the spacing, the more will be the effective pressure distribution. So that's why I have reduced the spacing value. Right. So here we have to provide, okay, provide 16 mm diameter bars, okay, 16 mm diameter bars at a spacing of 150 mm center to center. So this is how we can provide the spacing, or we can decide the spacing of the bar. So now let us calculate the area of steel provided. Okay, area of steel provided equals to, so how to find out that one? So 201.06, that is area of one steel bar of 16 mm diameter. So when you do pi by 4 into 16 square, you will get 201.06 divided by spacing. Let's say here the spacing is 150 mm. So let me go with 150 mm spacing into the width of the footing, which is 2800. 2800. So the value will become 5629.75 mm square. So this is the area of steel that we have to provide. Okay, this is the area of steel that we have to provide, or area of steel provided. Right. So from this, we are going to calculate the percentage of steel. So how to calculate the percentage of steel? PT equals to AST divided by B into capital D. So what is AST? AST is 5629, the provided area of steel. So 5629.75 divided by B, that is width of the footing, 2800, into the overall depth, which is 600. If you do in terms of 100 multiplied by 100, you will get in terms of percentage, that will be 0.34% of steel is required. So based on this calculation, we have to verify whether the depth whatever we have provided is safe enough in the shear criteria or not. So that we have seen in the last session, same calculations, nothing much changes happens here. But anyways, I'll talk about those things. So this is how we can decide the depth of the footing based on flexural criteria. What is meant by flexural criteria? It is nothing but we are going to find out with respect to the moments. Okay, that's what flexural criteria. Now we need to find out with respect to the shear criteria. So that's our next step. So shear check. So how to check for the shear? We have two types of shears. The first one is called as one-way shear. Okay, let me write that, check for one-way shear, and we have two-way shear also. So in both considerations, we have to check. So we have to check for one-way shear, and we also have to check for two-way shear as well. Right. So first, let us look for one-way shear calculation. Okay, let us look for one-way shear calculation. Now, we have discussed in the last session the one-way shear. What is the critical section distance for one-way shear? The critical section for one-way shear will be acting at a distance of D from face of the column. From face of the column on all sides. On all sides. Right. So this is where the critical section will be acting. So if you remember the image that I have shown you in the last session, this one. Okay, forget about the dimensions here. Let me just crop it. So the check for one-way shear will be acting at a distance D from face of the column. Right. So this is the distance D that is acting at the face of the column. Right. So now we have to find the distance D. Okay, that we'll find it out. But first, let us check for the shear force criteria. So how to check for the shear force criteria? So capital V shear capital V equals to upward soil pressure, same formula, upward soil pressure times of width of footing, okay, width of footing into L minus A, that is length of the footing, minus A, that is side of the column, divided by 2 minus depth of the footing, that is effective depth, not the overall depth. So L minus A by 2 minus D, that's the formula. Okay, but for rectangular footing, we have to calculate the one-way shear along the length direction and also along the width direction. If you remember, let me just show you that we have discussed in the last session. So we have calculated the one-way shear both along the length direction and width direction. Why? Because in rectangular footings, the length and width of the footings will get different. Okay, let me show you that. Yeah. So shear check for one-way shear. So here we have calculated the one-way shear along the length of the footing, and we have calculated the one-way shear along width of the footing. Why we have calculated? Because since it's a rectangular footing, the dimensions gets changed. The value of D gets changed. But in this case, it's a square footing and square column. So since it's a square footing and square column, the distance D will remain same. So that's why you can calculate for either L minus A by 2 or B minus B by 2. Anything you can do because the dimensions will not get changed. So therefore, capital V equals to upward soil pressure is 196.43 into the L value. What is L? L is length of the footing. That is 2.8. Sorry. First, we have to go with width of the footing, that is 2.8 again, into the length of the footing, 2.8 minus A. What is meant by A? A is the side of the foot column. Okay, A is side of the column. So what is the side of the column? Since it's a square column, it has equal sides, that is 0.4, which is given in the question, divided by 2 minus the effective depth. What is effective depth? 542 mm. So let me keep it in meters. That will become 0.542 meters. So from this, we can calculate the shear force value, which will be 361.9 kilonewtons. Okay, this is the shear force. But this shear force is not sufficient because we have to go with factored shear force, that is Vu equals to 1.5 times of 361.9 kilonewtons. Okay, 361.9 kilonewtons. So that will give us 542 542.85 kilonewtons of factored shear force. So from this factored shear force, we have to check whether tau v is less than tau c, and that criteria we have to check. So in order to check that, we have to solve for tau v. So how to calculate tau v? Tau v equals to Vu divided by Bd. Okay, Vu divided by Bd. So what is Vu? 542.85 into 10 cube. Let me keep it in terms of newtons, right? Vu divided by B. What is B? Width of the footing, that is 2800, divided by, sorry, multiplied by depth of the footing. What is depth of the footing? 542 mm. So therefore, you're going to get the tau v value as 0.358 megapascals. Okay, this is what tau v value. Now we have to look for tau c value. So how will you calculate tau c value? It is based on percentage of steel. Tau c is based on percentage of steel. Percentage of steel. So we have already calculated the percentage of steel, that is PT value. PT value, that is percentage of steel. So what is the value of PT? So if you just go with that, let me check that. Yeah, it is 0.34 percentage. So percentage of steel PT equals to 0.34 percentage. So at 0.34 percentage of steel, we have to find out the tau c value. Okay, we have to find out tau c value. So how will you get the value of tau c? That is from as per IS 456. Okay, as per IS 456 2000, IS 456 2000, clause number 40.4. Okay, clause number 40.4. I think page number 58, I guess. So let me just check with the previous problem. Table 19, I think so. Let us just check, and then I'll show you the table. Yeah, table 19. So we have to, this one I was talking about. Okay, so table 19, if you check, so instead of page number 9, I'll just make it as table 19. So once you check this page number, table 19, you can get the values of PT. So here, let me just show you those things. Let me just give me a second. I'll just share my screen with IS 456. Right. I hope you are able to see the IS code book. Let me just go to table 19 of IS 456 2000 so that we can calculate the tau c value. Let me just. That. Yeah, this one. So I hope you are able to see this table 19. Okay. So here, what is our percentage of steel? Our percentage of steel is 0.34. Okay, 0.34. But can you find the value for 0.34 directly? No. And the grade of concrete is M20 is the grade of concrete. Okay, in our case, the grade of concrete is M20. So our case is 0.34. So we don't have the value of 0.34 here, but 0.34 lies in between 0.25 and 0.5. That means For 0.25, the value of tau c is 0.36, and for 0.5, the value of tau c is 0.48. So when you interpolate these two, you're going to get the value of tau c when pt equals to 0.34. So let me write that one. Let me go with the table. I'll just write that table here. Just a second. Just copy this one. Yeah. So these are not the values. Right. So PT, that is 0.25. Okay, for PT is 0.25, and here it is 0.34, and then we have it for 0.5. Let me check the values. When PT equals to 0.25, let's see what is the value of tau c. So PT is 0.25. Okay, here you can see the value of tau c is 0.36. And for 0.5, the value of tau c is 0.48. So let me write those values there. So 0.36, and for 0.34 we have, sorry, 0.34 we have to find it out, and then for 0.5 it is 0.48. So once you do the interpolation, so I'll not go into the details of interpolation. So once you do the interpolation, you're going to get the value of tau c. I'll just make it as tc here. Tau c equals to 0.403. Okay, this is the how the value will be obtaining from. So now, based on this tau c calculation, we have to verify with tau v. So what is the calculation here, or what is the consideration here? If tau v is less than tau c, okay, then it is safe. The provided depth is safe in shear also. So if tau v is less than tau c, then the provided depth, the provided depth of the footing is safe in one-way shear. Let us check that. So what is tau v value? 0.358. What is tau c value? 0.403. So tau v is less than tau c or not? Yes, it is less than. Tau v is less than tau c. So therefore, the provided depth is safe in shear. So hence safe. Okay, it is safe only in one-way shear. Similarly, we have to do it for two-way shear also. So how to do it for two-way shear? So we have to look for the consideration. So let me write that value 4.2. Right. So next step is check for two-way shear. Check for two-way shear. So how to check for two-way shear? What is the critical section of two-way shear? The critical section, okay, the critical section for two-way shear will act at a distance of d by 2. Okay, at a distance d by 2 from face of the column. At a distance d by 2 from face of the column on all sides. But since it's a square footing, there won't be any problem. So on all sides. Right. So now let us find out the shear force value for two-way shear consideration. So capital V equals to upward soil pressure, okay, upward soil pressure into the width and length of the footing. That is area of footing, you can say. So B into L minus 0.4 into D, sorry, 0.4 plus D. I'll just write this one and then I'll show you what exactly I'm doing here. 0.4 plus D. Right. So this is the formula. So what is this one? How we are getting this one? So usually for one-way shear, for two-way shear, if you look into this particular figure, yeah. So forget about the dimensions that are available here. So don't think about the dimensions here. So what is this length? This side of the column, it is 0.4. This side of the column is also 0.4. So 0.4 plus D. How D is coming? D by 2 plus 0.4. Let me write that. Let me show you that. So D by 2. Okay, along length I'm calculating. That is along this length. So we have to find out this length. Okay, so D by 2 plus this length of the column or this side of the column. What is this side of the column? 0.4 plus this D by 2. So this side also it will be d by 2 only, right? So d by 2 plus d by 2 is d. Okay, that will be d by 2 plus 0.4, that is length of the column, plus d by 2. So that will become 0.4 plus d. Okay, that will become 0.4 plus d. So that's where I have written. So along length also 0.4 plus d, along width also it will be the same. Why? The dimensions of the column and the dimensions of the footing are same, since it's a square column and square footing. So that's where I have written it as 0.4 plus d here. Okay, this one 0.4 plus d into 0.4 plus d along length, and this is along width. So this one is along length consideration, and this one is along width consideration. So that's how we have to calculate the upwards two-way shear force. Okay, capital V value. So therefore, from this we are going to get the values of capital V. Okay, upward soil pressure is 196, width of the footing is 2.8, and length of the footing is 2.8, and the D value, that is 542 mm, that is 0.542. So once you solve this one, you're going to get the value as 1365.7 kilonewtons. But we have to look for factored shear force, that will be Vu equals to 1.5 times of 1365.7. That equals to, if you solve this one, you're going to get the value as 2048.56 kilometers. So this is the factored shear force. Now the next thing is we have to calculate the perimeter length. Okay, perimeter length of shear area. Perimeter length of shear area. So I'm just representing with B dash, just like the previous thing. So here, how to calculate the perimeter length? So 0.4, okay, 0.4 plus D into how many sides it is there? 4 sides, because it's a square column. So this side, it is one side. Let me write that. So this is one side, this is another side, this is another side, and this is another side. And all the 4 sides are same. So you can directly multiply with 4. So therefore, 0.4 plus D into 4. Okay, 0.4 plus D into 4. Why? Because on all the 4 sides, the sides of the column or the sides of the footing is same. So 0.4 plus D. What is D value? D is 0.542 into 4. Okay, when you solve this one, you're going to get the value as 3.768 meters, or you can make it as a 3768 mm. So this is the perimeter length of shear area. So from this, we can calculate the nominal shear at critical section. Okay, nominal shear at critical section. So how to calculate the nominal shear at critical section? That is tau V equals to Vu divided by, instead of B, we have to make it as a B dash into D. Okay, B dash into D. Same formula. Tau V equals to Vu by BD in one-way shear. If you see here, tau V equals to Vu by BD. But here, the B value gets changed based on one-way shear and two-way shear calculation. In one-way shear, the value of B will become the width of the footing or the length of the footing. But in two-way shear, the value of B will become B dash, which is the perimeter length. Okay, which is the perimeter length. So from this, we know the value of Vu, that is 2048.56, B dash we know, which is 3768 mm, and D we know, which is 542 mm. So if you solve this one, you're going to get the value in terms of megapascals as 1.003 megapascals. Okay, 1.003 megapascal. So this is the tau V value. Now, based on this, we have to calculate tau C also. Okay, we have to verify whether tau V is less than tau C or tau V is greater than tau C. So if you refer IS 456-2000, okay, as per IS 456-2000, if you remember, in the last session, I was talking about tau C into KS. Okay, I hope you remember that one. Let me just write the clause number. Clause 31.6.3. Yeah, 31.6.3, page number 58. If you refer this particular clause, we have the formula directly, that is shear at critical section. Okay, shear at critical section equals to tau C into Ks. Okay, tau C into Ks. So how to calculate the value of Ks? So Ks equals to, again, this formula is there in the code book itself, which I have shown you in the last session only. So 0.4 plus beta C. So I'll just make it as BC. Okay, instead of beta C, I'll just make it as beta C, BC. So how to calculate this beta C? Beta C equals to shorter side of column divided by longer side of column. Shorter side of column divided by longer side of column. So how to go with shorter side of column? Both shorter side and longer side, they have same values. That is 400 divided by 400, that equals to 1. So if beta C value is greater than 1, you have to take directly 1. If by any chance, if it is less than or equals to 1, then you have to take that particular value. This we have seen in the last session. So therefore, beta C equals to 1. If it is greater than 1, you reduce it to 1 only. Okay, don't go with anything else. Right. So here, next thing is Ks value. So Ks equals to 0.5 plus beta C. What is beta C value? 1. So 0.5 plus 1 is 1.5. So since the value of Ks, okay, since the value of Ks is greater than 1, hence we have to limit Ks equals to, okay, we have to limit Ks equals to 1 only. Sorry, here it is not, I told it in a reverse way, not for BC, I mean, not for beta C, but for Ks. Okay, whatever the beta C value that you are getting, you have to take that only, but Ks value I have to take. So I told it in opposite way. Right. So therefore, tau C equals to, we have a formula that is 0.25 times of root FCK. Okay, FCK power 1 by 2, I'll just make it as, instead of root, I'll just make it as 1 by 2. Right. So 0.25 root FCK. So FCK value we know, which is 20, that is grade of the concrete. So if you solve this one, 0.25 into 20, therefore you're going to get some value which is as tau C value. That will be 1.118 megapascals. Okay, so from this we have to verify whether tau V is less than tau C or not. So what is tau V value? 1.003. What is tau C value? 1.118. So tau V is less than tau C value. So what does it mean? Since tau V is less than tau C, since tau V is less than tau C, the provided depth is safe in two-way shear also. Two-way shear also. Hence, you can make this statement. Hence, the provided depth, okay, the provided depth, that is capital D equals to 600 mm, is safe for the design of footing. For the design of footing. So this is how we can say the depth is safe against the shear criteria and also the flexure criteria. It is not important that if it is satisfying only the flexure criteria, the depth will not be safe. So it has to satisfy whatever the depth that we are talking about, that depth has to satisfy both the shear criteria and also along the flexure criteria as well. So the final design details, you can say final design details. So what are the final design details? We have to write the length of the footing, width of the footing. So length of the footing, LF equals to width of the footing, BF equals to 2.8 meters. Okay. And the reinforcement. So provide 16 mm diameter bars at a spacing of 150 mm center to center. So this is how you can finalize. So that's the entire process of design. The design of isolated square footing. So in the next session, we'll be talking about design of sloped footing or combined footing. Anyone will check out. But tomorrow we don't have any class because every Saturday and Sunday both are holidays. So we'll meet on Monday's session. Okay. So if anybody is having any doubts, you can unmute and ask the doubts. Thank you.